and design considerations, another on materials. In case of design, there are several design considerations I have discussed: strength, stiffness, safety, assembly point of view, power, efficiency, etc., etc. But in case of mechanical member, first and most important design consideration is strength. That component can sustain the applied specified load. The maximum load to which the component can be subjected is given in the specification. Now it is the designer's responsibility to select the material and dimension and shape in such a way that under the maximum load it will not fail. Material can sustain the applied maximum load. So strength is the most important concern of designer. And to ensure the strength, designer has to know the material behavior under load. Under the given condition, given environment. So material behavior under the given load requires to know the strength of material formulation, because in your strength of material classes you have already gone through the behavior of a material, response of a material under load. You know, whenever load is applied to the material, if material is free to move, it is not constrained, then it will receive motion by the application of load. And during the motion, the force generated due to acceleration of the body will counter the applied force, and thus equilibrium will be developed. Because of the acceleration, force will be balanced. But if the component is restricted to move, but if load is applied, then deformation will take place. And due to deformation, strain inside the material will be developed. Strain is nothing but deformation per unit dimension. And due to the strain, stress will be developed inside the material. Resistance against strain and deformation will be developed due to microstructural behavior of the material. And now this stress multiplied by the area will generate reaction force against the applied load. Until the generated reaction force counters or balance the applied load, deformation will continue. At the final stage of deformation, the stress developed multiplied by the area provided can counter the applied load. So again, some equilibrium will be achieved. Because until equilibrium is achieved, responses will continue to change, will be in dynamic behavior. But in static equilibrium situation, there will be a final deformation, final strain, final stress, so that stress multiplied by the area can counter the applied load and equilibrium can be achieved. And through this period, amount of deformation, nature of deformation will vary from or will depend on nature of the load applied, shape of the material, material nature, etc. and etc. And depending on the deformation, strain will be developed. Depending on the strain, stress will be developed. And ultimately, stress multiplied by the area will counter the. So what we have to study, first of all, we have to know under a given load, depending on the geometry of the component, what type of stress will be developed, what type of stress or strain will be developed. First of all, we have to know the strain, and then if we can develop a material model which gives you the stress-strain relationship, then you can evaluate stress from strain. If you can develop a material model, then you can evaluate stress from strain. This is called stress-strain relationship. Stress-strain relationship comes, or rather depends on the type of material, type of loading, etc. and etc. So as a designer, what prerequisite is that under the given load, what type of deformation, what type of strain will be developed, and for this kind of strain, what will be the nature of stress, magnitude of stress, that designer has to know, has to evaluate during design. And therefore, he requires to know the stress analysis. Is my point clear or not?
Yes, sir.
Clear, sir.
And after knowing the stress, the designer has another inquiry. What is the limit of that stress that a material can sustain without failure? So that is another material testing part, material property part. And if a designer knows this material property, either consulting from catalog or directly experimenting in his own lab, if he knows the material property, then he knows the limit of stress which can be allowed for this particular material. And then designer has the scope to change the dimension suitably so that under the given load, the maximum stress developed will not exceed the permissible stress value for that material. That is the designer role. To evaluate maximum stress developed within the material, designer has to know the material behavior under load. He has to know what will be the nature of stress when a member is subjected to some axial type of loading. If the load is biaxial, what will be the nature of stresses? If the load is a combination of tensile and torsion, what will be the nature of stresses? If the load is a combination of torsion, tension, bending, all types of loading, because in real situation, the component may be under very complex type of loading. Axial, bending, torsion, every type of loading can be present within the member and will generate a complex stress scenario. From this complex stress scenario, designer role to find out the equivalent stress by which he can compare the material strength and can decide over the design dimensions. So this is the role of the designer. He use the knowledge of strength of material into design by this approach. Is the idea clear or not?
Yes, sir.
Therefore, I have, rather here it has been written review of stress analysis, as because this is not the part of your syllabus. This is already, you are exposed to this stress analysis in your strength of material classes. Only before going into actual application of this strength of material formula in design, just I like to review the methods or procedure which you have already done in your strength of material class. Okay.
Yes, sir.
Only for recapitulation. So we can start from a general idea, semi-general, because you know whenever a member is subjected to loading, every member is actually three-dimensional existence. But for modeling purpose, sometimes we assume a material to be 2D, 1D, etc., etc. But generally, or it is absolutely true that any material, any component is always 3D or three-dimensional. And within a point, at a point of that component, the stress distributions are also three-dimensional. Is it clear?
Yes.
Yes, sir.
On the basis of one assumption that the material is isotropic, follow the word, material is isotropic. What is meant by it? Stress-strain relationship. Stress-strain relationship of the material is uniform in any direction. It doesn't depend on the direction. Shall I repeat?
No, sir.
If material is isotropic, then stress-strain relationship is independent of direction, and therefore sum of the material coefficients can be cancelled and the stress matrix can be arranged by a 3 by 3 matrix, total 9 member. The stress scenario can be represented by 9 member. Is it okay?
Yes, sir.
Yes, sir.
In case of anisotropic material, where we cannot assume that material stress-strain relationship is independent of direction, there are 36 components are there. To describe the stress situation in a material, we require 36 components without any assumption. But by the basis of assuming the material to be isotropic, we can reduce the number of stress components to represent a stress situation at a point within the material into 9. Is it clear or not?
Clear, sir.
Yes, sir.
Sir, 36 কিভাবে হচ্ছে একটু বলবেন?
36 হচ্ছে আমার যদি কোইফিসিয়েন্ট গুলো ধরি না, তখন কোইফিসিয়েন্ট গুলো হয়ে যাবে কি, ধরো ইলাস্টিক মডিউলাস, ঠিক আছে? ফর দিস মেটেরিয়াল ইলাস্টিক মডিউলাস তো একটাই ধরছো তুমি, নর্মাল স্ট্রেস ভার্সেস নর্মাল স্ট্রেন। ওকে, হ্যালো,
Yes, sir.
Yes, sir.
নর্মাল স্ট্রেস ভার্সেস নর্মাল স্ট্রেন, এই যে রেশিওটা, এই রেশিওটাকে তুমি একটাই ধরছো একটা মেটেরিয়ালের জন্য। এক্স ডিরেকশনে আলাদা, ওয়াই ডিরেকশনে আলাদা, জেড ডিরেকশনে আলাদা, বা তার কোনো অ্যাঙ্গুলার প্রভিশন আছে, এগুলো ধরছো না, অ্যানাইসোট্রপি ধরছো না।
বুঝেছি স্যার।
তখন ওই কলামগুলো, ওই মেম্বারগুলো ভ্যানিশড হয়ে যায়, ওই ভ্যারিয়েশনটা লাগে না। তুমি ডিটেলে পড়বে, তুমি যদি এটা একটা কোনো বই ফলো করো, তুমি এই টিমোশেঙ্কোরই থিওরি অফ ইলাস্টিসিটি একটা বই আছে, ঠিক আছে? সেই বইয়ে 36 থেকে শুরু করে কিভাবে ওটা রিডিউস টু 9 হয় দেখিয়েছে, দেখবে অ্যানাইসোট্রপি থেকে আইসোট্রপিতে গেলে। আন্ডারস্টুড?
Yes, sir.
এবার as because there is equilibrium, at equilibrium state another condition is satisfied, that tau xy and tau yx দুটো আছে, দেখো tau xy আর tau yx। tau xy হচ্ছে এই ফোর্সটা শিয়ার ওভার xy প্লেন, ঠিক আছে? আর tau yx হচ্ছে এইটা। যেহেতু ইকুইলিব্রিয়ামে আছে, রোটেশনাল ইকুইলিব্রিয়ামে আছে, তাই টাউ yx আর টাউ xy ইকুয়াল হতে হবে। ডু ইউ এগ্রি অর নট? Because about the z axis torque is given by, look, tau xy into this dimension and tau yx into this dimension, and now they will be equal. একটা ক্লকওয়াইজ আছে, একটা কাউন্টার ক্লকওয়াইজ আছে, তাই তো?
Yes, sir.
হ্যাঁ হ্যাঁ
So if we assume the equilibrium, then another assumption is automatic, that tau yx and tau xy are same. If we know tau xy, we can evaluate tau yx. No problem.
তাহলে স্যার ইকুইলিব্রিয়ামে স্যার নটা তো তাহলে স্যার ইন্ডিপেন্ডেন্ট নয়, তাহলে তো স্যার 6টা ইন্ডিপেন্ডেন্ট।
আমি তো সেটাই পরের লাইনে বলতাম আর কি।
ও আচ্ছা।
So for another assumption that equilibrium is there, at equilibrium state actual unknown variation, unknown quantity to represent the whole stress situation at a point for isotropic material under equilibrium is given by 6 member. 3 normal stress, sigma xx, sigma yy, sigma z, and 3 shear stress component, tau xz, tau yx, and tau xy. Sorry, tau yz. It is clear.
Yes, sir.
Now, sometime for analysis, we may consult stress on a plane only. On a plane. Naturally, there it is assumed that in the third direction there is no stress at all. So again, stress component will be reduced. Instead of sigma xx, sigma yy, sigma zz, suppose it is in xy plane, then sigma xx and sigma yy will be there, sigma zz will be vanished. Do you agree?
Yes, sir.
Yes, yes, sir.
So this is called plane stress situation. Plane stress situation. Now somebody can ask, is it possible that member is loaded externally in three directions, but within the material along certain plane, there is no stress in the perpendicular direction of the plane? The answer is yes. And then we call that it is a plane stress situation along that plane in the member at this point. Plane stress situation. Do you agree?
স্যার একবার বলুন।
Yes, sir, এটা বুঝতে পারলাম।
Suppose we observe that we take a slice in a member, within a member at a point along certain orientation. And we find that finally the load perpendicular to that particular section or plane taken is zero. There is no stress in the third direction. Then stresses are only in two directions, two orthogonal directions.
Yes, sir.
So stress system there can be represented by a 2D representation
Yes, sir.
as shown here. This stress situation is called plane stress situation. This term is very important. In future, as a mechanical engineer, in case of material behavior, you will face this what? Plane stress situation. Now compile. Plane stress, that means on that plane, stress can be represented two-dimensionally. That means in the perpendicular direction of the plane, there is no stress at all. It is convenient because, of course, instead of 3D, 2D representation will require minimum number of unknown, minimum number of stress components. But I will not do it forcibly. If it is available, then I will do it. I will take the advantage. But as an engineer, as a designer, I should have this knowledge that there may be plane stress situation in the member at certain situation. And if it is there, I will take the advantage of plane stress situation. Or rather, I will convert the analysis method into 2D system instead of 3D. Do you agree or not?
So এটা স্যার মানে কোন সিচুয়েশনে হবে যে আমরা প্লেন স্ট্রেসটাকে
Another important question comes. Let us see some practical example. Suppose a very thin sheet. Okay.
Yes, sir.
Now you are applying load on the surface in the perpendicular direction. Okay.
Yes, sir.
Material is tried to be extended in that direction. And every material pulls the next member towards its direction. Is it true?
Yes,
Yes,
sir.
sir. Yes, sir. Yes,
And
sir.
member is strained only if it is pulled by two directions. Do you agree?
Yes, sir. Yes, sir.
Member inside the component, not on the surface, always have surfaces on its both sides. Do you agree?
Yes, sir.
So it will be pulled in opposite direction by the two adjacent layer of that section. Do you agree?
স্যার একটু
Hello?
মানে ভিজুয়ালাইজেশনের প্রবলেম হচ্ছে, একটু স্যার মানে ড্র করে বলতে পারবেন?
হ্যাঁ, ড্র করবো কি করে বাবা? Try to visualize. A thick plate of thickness T is taken and load is applied on this member. Okay,
ওকে স্যার।
in the x direction supposed to be.
মানে
Yes,
স্যার
sir.
ওটার পারপেন্ডিকুলার মানে এক্স ডিরেকশন
আচ্ছা, এইখানে দেখতে পাচ্ছ, আমার এখানটায় দেখা যাচ্ছে যেটা নাড়াচ্ছি pointer?
হ্যাঁ স্যার, হ্যাঁ স্যার।
আচ্ছা, ধরো এটার একটা থিকনেস আছে, এই 3D মেম্বারটায় দেখো, আমি
হ্যাঁ স্যার বুঝেছি।
জেড ডিরেকশনে পুল করছি ওপর নিচে, ক্লিয়ার?
ইয়েস স্যার।
তাতে কি হবে? মেটেরিয়াল কন্ট্রাক্টেড হবে তো সাইড থেকে, বাই পয়জন রেশিও, বাই
ইয়েস স্যার।
হবে তো?
ইয়েস স্যার, ইয়েস স্যার।
আচ্ছা, এইবার এই যে জেড ডিরেকশনে টানছি, যার ফলে আমার সাপোজ টু বি এটা ওয়াই ডিরেকশনে মেটেরিয়াল কন্ট্রাক্টেড অথবা এক্সটেন্ডেড হচ্ছে, সেটার জন্য কি করতে হবে? যদি একদম বাইরের সারফেসটা ধরো, একদম বাইরের সারফেসে তো দুদিকে সারফেস নেই, আছে?
না স্যার, একদিকেই আছে।
তাহলে ওইখানটায় স্ট্রেন তৈরি করা কি সম্ভব?
না। আচ্ছা।
ওই দিকটায় ওই ডিরেকশনে স্ট্রেন
না স্যার, এটা ফর্টিফরমেশন হবে না স্যার।
স্ট্রেস
না।
তৈরি হবে কি করে?
হ্যাঁ স্যার।
ফলে ওপেন সারফেস সব সময় প্লেন স্ট্রেস সিচুয়েশনে থাকবে। ডু ইউ এগ্রি?
ইয়েস স্যার।
হ্যাঁ স্যার।
কিন্তু মাঝখানটায় যে আছে ইনসাইড দ্য মেম্বার, দ্যাট সেকশন হ্যাভ এ ক্রস সেকশন এট দ্য লেফট সাইড, এট দ্য রাইট সাইড, বোথ,
ইয়েস স্যার।
and they will apply force on the opposite direction, so strain will be developed.
ইয়েস স্যার।
Shall I repeat or it is clear to you?
বুঝতে পেরেছি স্যার।
So depending on the orientation of the plane, position of the plane, it may happen that the stress components in a certain axis or along certain direction is not at all there. If it happens, then the advantage is it is a specific case of stress situation, and it is advantageous plane stress situation for analysis. So engineers attempt will be, if possible, if justified, to represent the stress state as a plane stress to reduce the hazards of number of components. And as an engineer, you should have an open eye within the component where we are rather interested to analyze the system. Is it plane stress? Then it is advantageous. If it is justified to assume it plane stress, you will assume it. Otherwise, you will do 3D analysis. Is my point clear or not?
ইয়েস স্যার।
Another extreme situation is called plane strain situation. Then what happened that in this component, stresses will be in all the directions in a particular plane. All the directions stresses will be there, but because of the combined strain, because force on the y direction will create negative strain in the x direction, and if there is some x direction strain and these two are equal and opposite, then finally strain in the x direction will be nullified and will be zero.
Yes, sir.
Yes,
But
sir.
stresses are present in all the direction. What I try to convey you as because lateral contraction, or rather these are possible, so you should not be confused that if strain is there along certain axis, then only stress is there, or if stress is there, there must be strain along that direction. Is my point conveyed or not?
ইয়েস স্যার।
It may happen that along certain direction, stress is very much present, strain is absent. And the reverse is also true. Strain is very much present, but there is no stress because it is the combination. Ultimate, what will happen that we have to know from the analysis. Only I will try to make you understand that there may be extreme situations like plane stress, plane strain. But in most of the cases, situation will be strain, stress, all are present in all the direction with different magnitude. Plane stress and plane stress situation are two extreme situations. Shall I repeat?
No, sir.
Understood?
Yes, sir. Understood.
Yes, sir.
So let us change our topic. First of all, I believe that if I discuss keeping the expression analysis in 2D mode, you can extend it to 3D mode. I believe. For understanding, for visualization, I will take the help of biaxial stresses, biaxial analysis. Should I move?
Yes,
Yes,
sir.
sir.
Yes, sir. So suppose a member is subjected to some external forces, X direction, Y direction, and there is also shear stress also. Now, the value of normal stress and value of shear stress on a plane, if we like to calculate, then we have to take the orientation of the plane with reference to the some geometric axis of the body. I think that you have done in your biaxial analysis.
Yes, sir.
Yes,
Yes,
sir.
sir.
And if the orientation of the plane is given by an angle phi, phi is the angle with the x-axis, then the normal stress on that plane is given by, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 phi plus tau xy sin 2 phi. এটা পড়েছো তো?
Yes, sir.
Yes, sir.
এইখানে অ্যাপ্লাইড লোড গুলো দেখো, সিগমা এক্স দেওয়া আছে, সিগমা ওয়াই আছে, আর টাউ এক্স ওয়াই টাউ ওয়াই ওয়াই এক্স আছে। এবার আমি এখানে একটা প্লেন নিলাম এই অ্যাঙ্গেলে, যেখানে অ্যাঙ্গেলটা ফাই দেখিয়েছি। ক্লিয়ার? এবার এই হচ্ছে আমার নর্মাল স্ট্রেস আর এই হচ্ছে আমার শিয়ার স্ট্রেস অন দ্য গিভেন প্লেন। তার এক্সপ্রেশন হচ্ছে এইটা। এটা তোমরা শিখেছো তো অলরেডি?
হ্যাঁ স্যার, এখান থেকে তো স্যার সার্কেলের ডেরিভেশনটা আছে স্যার কো।
আচ্ছা, আর যদি কারোর গ্যাপ পড়ে থাকে তাদের জন্য আমি আরেকটা মেটেরিয়াল আপলোড করে দিয়েছি ফর ইওর ইন্টারেস্ট, বাইঅ্যাক্সিয়াল স্ট্রেস অ্যানালিসিস বলে, যেখানে ডেরিভেশনটা একেবারে ডিটেলে দেওয়া আছে। ঠিক আছে? তো যারা ইন্টারেস্টেড ফার্দার দেখার জন্য তারা ওইটা একবার দেখে নেবে। ডেরিভেশনটা একেবারে লাইন বাই লাইন ধরে করা আছে। ইজ ইট ক্লিয়ার?
ভালো, তো সবার রিভিশন হয়ে যাবে স্যার।
হ্যাঁ
হ্যাঁ, স্যার।
তোমরা ওই মেটেরিয়ালটা একটু গো থ্রু করো। আমার ধারণা ওইখানটা এই যে এক্সপ্রেশনটা পেয়েছি এটার একটা ডেরিভেশন আছে,
হ্যাঁ
লোড
স্যার,
ব্যালেন্স করে ইকুইলিব্রিয়াম ধরে করা আছে, সিগমা আর টাউ এর এক্সপ্রেশন। আমরা
Yes.
ডিজাইনার হিসেবে ইন্টারেস্টেড এক্সপ্রেশনটায়। ক্লিয়ার?
এই সেমিস্টারে আমাদের প্লেন স্ট্রেনের ডেরিভেশনটা আছে, তবে এটা স্যার একটু লিটল বিট কমপ্লিকেটেড এমনি ওই এই প্লেন স্ট্রেসের থেকে আর কি। ডিফরমেশন ক্যালকুলেট করে তারপর দেখলাম যে ডেরিভেশনটা করা আর কি।
দেখে নিও, যদি কেউ বুঝতে না পারো ইন্টারেস্ট ফিল করলে আমাকে পরে বলো, আমি বুঝিয়ে দেবো।
ওকে স্যার।
As a designer, we are starting from this expression, okay? That sigma means normal stress on a plane having angle phi with the x-axis is given by this. Look here, in the normal stress on the both direction xy and also shear stress are present. What designer can comment over it? That in an inclined plane, the value of normal stress depends on the applied normal stresses and shear stresses, all of the components. Agreed?
Yes, sir.
Similarly, shear stress also depend on normal stress and shear stress, if the plane is inclined, depending on the value of phi. Secondly, the magnitude of this normal and shear stress depend also on the orientation. Inclination changes, the value of shear and normal, both the stresses are changing. Clear?
Yes, sir.
As a material scientist, we are interested in all these stress components, all the values, variation, etc., etc. But as a designer, can somebody tell what will be our interest? As a designer, to know the stress component at all the points. or to know the maximum stress within the member under a given loading system.
To find the maximum stress in which orientation.
Obvious, because designer are responsible to satisfy the strain, and it is obvious that if maximum stress developed within the material is kept below the permissible stress of the material chosen, all the points will sustain the load, as because in other points stresses are below, lower. So designer interest, if a member is subjected to this kind of loading where the maximum stress can be developed, if I can get the expression of that maximum stress, my requirement is over. Do you agree or not?
Yes, sir.
So now designer try to find out the maximum possible value of sigma. Sigma x, sigma y, tau xy are given constant. So now it is a function of theta. So if we make del sigma del theta is equal to 0, that will give you some value of phi. If you write del sigma del phi is equal to 0, taking the derivative of this function and equating to 0, you can solve phi.
Yes, sir.
Yes, sir.
At that phi, the value of sigma will be extreme,
Yes, sir.
Yes, sir.
maximum and minimum. Because in both the cases, del sigma del phi 0. I think you know it, no?
Yes, sir.
So equating del sigma del phi equal to 0, we can solve for phi, and putting the value of phi's, because at two different phi it will be 0, and knowing those two phi, if we put in the equation, we will get this expression for extreme value of the normal stresses. When sigma is written as sigma 1, sigma 2, they are called extreme stresses, or popularly known as principal stresses. What are the principal stresses? They are nothing but the normal stress or extreme normal stresses in case of this kind of biaxial loading. This derivation is given there, but we are interested in the expression of principal stresses. And note it, at the plane where the value of normal stresses are extreme, where del sigma del phi 0, there the value of tau will be 0. Value of shear stress will be 0. Because if we know that phi, we can put the value of phi in the expression of tau, and we will get tau is equal to 0. Understood?
Yes, sir.
So designer's interest, the principal stresses. A member is subjected to a biaxial load or triaxial load. In case of triaxial load, there will be three principal stresses. So either triaxial, or I am referring to biaxial, you can extend it to triaxial also. There are two extreme stresses, one maximum, another minimum. Normal stresses will be obtained. Designer's interest is here. Clear? Hello?
Yes, sir.
But designer knows that sometimes it may happen that for a material, failure occurred not because normal stress exceeds the permissible normal stress of the material. Rather, shear stress developed within the material exceeds the permissible shear stress of the material. So now what should be designer interest? To know the tau max, isn't?
Yes, sir.
So again, we can equate del tau del phi 0 and can find out where the maximum tau occurs, and we will get the maximum value of tau plus minus, considering the magnitude wise, these are the maximum value, but one in positive sign, another is negative sign, plus minus. So here two extreme shear stresses are given. One, plus root over this, second minus root over this. Understood?
Yes, sir.
Look, this component is common, isn't? Hello? Same.
Yes, sir.
Mind it. Now, you know more circle, no?
Yes, sir. ওটাই স্যার রেডিয়াস আপনি যেটা দেখালেন।
Because the general expression of sigma and tau can also be written. If we assume this as R, then here we can write sigma is equal to sigma x plus sigma y by 2 plus R cos phi, and tau is equal to R sin phi. I think you know it, no?
Yes, sir.
So if x is given by a plus r cos phi and y is given by r sin phi, then this is the equation of a circle in parametric form having center at sigma x plus sigma y by 2 and of radius r. Do you agree with me or not?
Yes, sir.
That is the Mohr circle actually. The center is given by sigma x plus sigma y by 2. And this radius is given by root over sigma x minus sigma y by 2 tar whole square plus tau xy square. Is it clear?
Yes, sir.
Yes,
This
sir.
circle cuts the principal normal stress axis at 2 points, which gives the value of sigma 1 and sigma 2. And as it is cutting the normal stress axis, so here value of shear stress is of course 0. Is it true?
Yes, sir.
Yes, sir.
Can somebody tell me what is the value of normal stress at the plane where tau is maximum? Can anybody tell? Eh?
স্যার ওই তো সেন্টারটা মানে ওই
Very
সিগমা এক্স প্লাস
সিগমা এক্স প্লাস সিগমা ওয়াই বাই 2 ওইটা
Very good, very good. So as because at the center, actually the point will be lying along the center. So the coordinate of the center will give you the value of normal stress. So is it understood? Can somebody tell when the Mohr circle will have its center at the origin?
When there will be no shear stresses, only normal stresses are there, but they will be opposite in nature.
When sigma x, sigma will be equal and opposite in nature.
Yes, sir.
Yes, sir. That will opposite in nature.
Yes. So I think these points are known to you, no?
Yes,
Yes, sir.
Okay. Very good. It will be helpful. And from here, you have to know that tau 1, 2, tau 2, 3, and tau. It has been general expansion is given for 3D. If you look that this value of tau 1, tau 2 can be written, you know sigma 1 and sigma 2, no? If you find out sigma 1 minus sigma 2 by 2, sigma 1 minus sigma 2 by 2, that will give you the value of tau 1. So similarly, in three-dimensional stresses, three principal stresses are there, and mutual difference of these three principal stresses divided by 2 will give the magnitude of three extreme shear stresses value. Is it clear?
Yes, sir.
So this is also important, and you know the magnitude actually. So from this, depending on the value of sigma 1, sigma 2, sigma 3, which one of these tau 1, 2, tau 3, 2, 3 and tau 3, 1 will be severe, that depends on the value of sigma 1, sigma 2, sigma 3. Do you agree?
Yes, sir.
Yes, sir.
Now we can come back to very simple loading. Type of loading. If a member is axially loaded, you know normal stress, isn't? Hello?
Yes, sir.
Yes, sir.
I will again explain one thing, that critical point, critical section on the member. Suppose a member is there. Member is subjected to load. You will try to review what is the variation of the effect of stress along the section. From section to section, is there any variation? If there is a variation, then your interest will be which is the section where maximum stress will be developed. Is there any scope to identify? Because engineer requires answer of these questions, either from previous knowledge or by analysis. If a member is subjected to this kind of axial loading, can anybody tell that is there any critical cross section here? Which one is the critical cross section? Hello?
স্যার মানে ক্রিটিক্যাল ক্রস সেকশন বলতে মানে যেখানটায় স্ট্রেস কনসেন্ট্রেশনটা সবচেয়ে বেশি সেরকম জায়গা বলছেন স্যার?
ক্রিটিক্যাল ক্রস সেকশন মানে আমার ডিজাইনার হিসেবে ইন্টারেস্ট হচ্ছে ম্যাক্সিমাম স্ট্রেস সেটাকে খুঁজে বার করা। ম্যাক্সিমাম স্ট্রেস খুঁজে বার করতে গেলে একটা প্রশ্ন প্রথমত আসবে যে ক্রিটিক্যাল ক্রস সেকশনটা কোথায়, কোন ক্রস সেকশনে ম্যাক্সিমাম স্ট্রেস হতে পারে।
মানে স্যার এখানটায় যেখানে দেখতে হবে মোট সার্কেলে স্যার প্লেনটাকে লোকেট করলেই বুঝতে পারবো যে কোন ক্রস সেকশনে হচ্ছে ম্যাক্সিমামটা আসছে স্যার।
So I think sir 45 degree হবে কারণ
More circle will give you orientation, not the cross section. এই মেম্বার থেকে বলো মানে ক্রিটিক্যাল ক্রস সেকশন প্রথমত এই যে সারফেসটা যার উপর লোডটা অ্যাপ্লাই হয়েছে, আমি যদি তাকে ক্রিটিক্যাল বলি তোমার আপত্তি আছে? এই মেম্বারের মধ্যে আর কোনো প্লেন আছে যেখানে এর থেকে বেশি নর্মাল স্ট্রেস অথবা শিয়ার স্ট্রেস তৈরি হতে পারে?
না স্যার।
তাহলে দেখো আমি প্রথমত বলতে পারি ফার্স্ট এনি ক্রস সেকশন পারপেন্ডিকুলার টু দ্য অ্যাপ্লাইড লোড আর ক্রিটিক্যাল and equally critical if normal stress is concerned. Can I pass this statement?
ইয়েস স্যার, একদম স্যার।
Yes, sir.
Critical and all the cross sections along these directions are equally critical.
ইয়েস
All of them are equally critical. What is the conclusion? Conclusion, designer can take normal stress at any cross section perpendicular to this load. That will serve the purpose confidently. Is it okay?
Yes, sir.
Now you have been asked, design a member 20 millimeter circular rod. Okay. Suppose 20 millimeter is not given. It is given that you have to design a circular rod which can carry 100 kilonewton and material property is given that the maximum normal stress it can allow 300 MPa or 400 MPa. Now you have to design. Before designing, you have to investigate. Okay, this is the loading pattern. What is the cross section where I should calculate the stress? That means what is the cross section where the maximum stress can be developed? Okay, look. And now from your knowledge, from your observation, you are confident, okay, any cross section in the perpendicular direction is a critical cross section. So stress on that cross section requires to be calculated and to be checked against material property. Isn't?
Yes, sir.
So you pi d square by 4. P divided by pi d square by 4 will give you the value of normal stress developed on that cross section and you check against the material property. Find out the value of D. Am I right?
Yes.
So here it is given, I think you can understand this. I will not repeat again. Here some examples are here for shear stress. Okay. rivet joint. When they are pulled in the opposite direction, then rivet can shear along this. So P by pi d square by 4 will be the shear stress, and that will be compared with the allowable shear stress for the material. Am I right?
Yes, sir.
Yes.
Yes, sir.
Some problem are given. I think you will go through and you can understand. Here given torsion. Again, I will ask the question, which cross section is critical?
Sir, outer cross section.
Eh? Outer surface, outer the cross section. Torque is equal along any cross section. Do you know that? Throughout this length, if you choose any cross section, the amount of torque applied over that cross section is same. Do you agree or not?
সেমই তো হবে স্যার, ওটা তো ফ্রি ভেক্টর বলে মুভ করাতে পারে।
এই যে রডটা আছে, আমি একটা এন্ড ফিক্স করে আর একটা এন্ডে টর্ক দিয়েছি। তো প্রথম লেয়ারটা টর্ক তার পাশের লেয়ারকে দিচ্ছে, তার পাশের লেয়ারটা তার পাশের লেয়ারকে দিচ্ছে। এভরি লেয়ার আর অফারিং অর রিসিভিং টর্ক ফ্রম ইটস অ্যাডজাসেন্ট লেয়ার এন্ড অফ ইকুয়াল অ্যামাউন্ট অফ টর্ক। এন্ড আলটিমেটলি লাস্ট যে ক্রস সেকশনটা আছে তাকে এই সাপোর্টটা টর্ক সাপ্লাই করছে উল্টো দিক থেকে, দিয়ে কাউন্টার ব্যালেন্স করছে, আবার উল্টো দিকে আসছে টর্কটা, ইকুইলিব্রিয়াম তৈরি হচ্ছে, তাই তো?
Yes.
তার মানে এনি ক্রস সেকশন উইদিন দিস মেম্বার তার দুটো দিকে দুটো সারফেস আছে, দুটো সারফেসে ইকুয়াল এন্ড অপোজিট টর্ক আছে। ডু ইউ এগ্রি অর নট?
ইয়েস স্যার।
এইবার তাহলে লেন্থ বরাবর কোন ক্রস সেকশনটা নেব এখানে ইরিলেভেন্ট। ক্যান আই পাস দিস স্টেটমেন্ট?
Yes, sir.
এবার ইম্পর্টেন্ট হচ্ছে when a circular body is subjected to torque, because of the torque, where maximum stress can be developed? At the surface?
Yes, sir.
Any point on this surface. দেখো, যেহেতু any cross section is equally critical, সেহেতু any point on the surface are equally critical, তাই না? Regarding shear stress developed due to applied torque, any point is equally critical. Do you agree or not?
ইয়েস স্যার।
Now another thing can happen, that bending stress, এটাও পড়িয়ে দিই, বলে দিই, এটা তো তোমরা পড়েছো তো?
হ্যাঁ স্যার।
হ্যাঁ স্যার পড়েছি mainly।
Depending on the bending, one half remains in contraction, another half. About the neutral axis, half tensile, half compression. And on the surface, one extreme maximum tensile, another just 180 degree apart, another maximum compression. These things are already, I think, known to you.
Yes, sir.
And the
Yes.
value of bending stress, which is actually normal in nature, mind it. Bending stress, because here this normal stress is developed due to bending, so it is termed as bending. But by nature wise, it is equivalent to normal stress. By nature, it is normal stress. Do you agree?
Yes, sir. Yes, sir.
And
Normal
in a same member, simultaneously, compression and tension can take place, though they are normal in nature. Clear?
ইয়েস স্যার।
And value of this normal stress is given by three terms, M, Y, I. M is the applied bending moment, isn't it?
Yes, sir.
Y is the distance of the point from the neutral axis. And I is the moment of inertia. Is it true?
Yes, sir.
Yes, sir.
So ultimately, suppose a simply supported beam like this, two concentrated load on the member. If I say you take any cross section along the length, am I right? Hello.
Yes, sir.
Can we take, for stress analysis, can you take any cross section along this beam or along this bar? As we have observed in case of pure torsion and tension, tensile axial stress, that along the length there is no variation. Every cross section is equally critical. But in bending it is not true.
না স্যার ক্রস সেকশন
Bending moment স্যার চেঞ্জ হবে স্যার।
তাহলে ডিজাইনারের একটা এক্সট্রা রোল কি হবে?
ম্যাক্সিমাম বেন্ডিং মোমেন্টটা ফাইন্ড
ডায়াগ্রামটা ড্র করে করতে হবে
Very good. Depending on the structure, load, support, etc., etc., another finding for bending cases is to find out the cross section where maximum bending moment will be applied. এইবার সেইখানে y এর ভ্যালু কত, i এর ভ্যালু কত, এইগুলো বসালে আমি বেন্ডিং স্ট্রেস পেয়ে যাব এবং আমি জানি যে উপরে বেন্ডিং এর নেচারের উপর ডিপেন্ড করে একটা দিকে টেনসাইল একটা দিকে কম্প্রেসিভ স্ট্রেস তৈরি হবে। ক্লিয়ার?
ইয়েস স্যার।
আচ্ছা, আমি এখানটা একটু রিপিট করি এই মেম্বারটাকে ধরে একটু দেখি আমরা আলোচনা। সাপোজ ইন দিস কাইন্ড অফ মেম্বার এখানটা এটাকে ফিক্স করে দেয়া হলো, দিয়ে একটা অ্যাক্সিয়াল লোড দেয়া হলো। ক্লিয়ার?
ইয়েস স্যার।
তাহলে কোন ক্রস সেকশনটা ক্রিটিক্যাল হবে?
স্যার একবার কোশ্চেন একটু বলবেন স্যার।
সাপোজ এ মেম্বার, আচ্ছা তুমি এই বিমটাকে একটা ক্যান্টিলিভার বিম ভিজুয়ালাইজ করো, ভাবতে পারবে তো?
হ্যাঁ স্যার ভাবা যাবে। একটা এন্ড
এই এন্ডটাকে সাপোর্ট ধরে নাও, এখানটায় ধরো গ্রিপ করে রাখা আছে, এখানে সাপোর্ট নেই, একটা আছে। তাহলে ইউ নো দ্য বেন্ডিং মোমেন্ট উইল ভ্যারি, ম্যাক্সিমাম হচ্ছে কোথায়? অ্যাট দ্য সাপোর্ট, তাই তো?
হ্যাঁ স্যার।
নাও অ্যালং উইথ দিস বেন্ডিং লোড ইউ অ্যাপ্লাই সাম অ্যাক্সিয়াল লোড at this end.
হ্যাঁ স্যার।
Now which cross section is critical?
সাপোর্টে তাহলে স্যার ক্রিটিক্যাল হবে, কারণ ওখানে বেন্ডিং মোমেন্ট তো ম্যাক্সিমাম আর ওখানে অ্যাপ্লাইড স্ট্রেসটা মানে নরমাল স্ট্রেসটাও ম্যাক্সিমাম।
তাহলে নরমাল স্ট্রেসের রেসপেক্টে কোনো ক্রিটিক্যালিটি নেই, কিন্তু বেন্ডিং মোমেন্টের রেসপেক্টে যেহেতু আছে, তাহলে আলটিমেটলি সাপোর্ট ক্রস সেকশনটাই হচ্ছে ক্রিটিক্যাল। তাহলে উই রিকোয়ার টু অ্যানালাইজ স্ট্রেস অন দ্য সাপোর্ট এন্ড। ডু ইউ এগ্রি?
ইয়েস স্যার।
Yes, sir.
আচ্ছা, এইবার একটা ইন্টারেস্টিং কোয়েশ্চেন করছি। ওই সাপোর্টে ওপরের পয়েন্ট আর নিচের পয়েন্ট, এই দুটোর মধ্যে কোনটা ক্রিটিক্যাল হবে?
স্যার ওটা তাহলে লোডের উপরে ডিপেন্ড করছে যে আমি টেনসাইল লোড দিচ্ছি না কম্প্রেসিভ তার উপরে। যদি লোড টেনসাইল দিই তাহলে স্যার উপরের দিকটা তাহলে বেশি হবে, কারণ উপরের দিকটা তখন টেনসাইল মানে উপরের সেকশন
মানে উপরে নরমাল স্ট্রেসটা অ্যাডিটিভ হয়ে যাবে, দুটোই যেহেতু টেনসাইল,
আর নিচের দিকটা সাবট্রাকশন হবে যেহেতু স্যার নিচে কম্প্রেসিভ আর টেনসাইল।
আচ্ছা, ভেরি গুড। এবার আমি আরো কমপ্লেক্স করলাম, এই এন্ডে একটা টর্ক দিলাম, একই সাথে বেন্ডিং রইলো, অ্যাক্সিয়াল রইলো, টর্ক রইলো, তাহলে
স্যার টর্কটাকে তাহলে স্যার ইকুইভ্যালেন্ট বেন্ডিং মোমেন্টে তাহলে ট্রান্সফার করে নিয়ে তারপরে ক্যালকুলেশন।
কেন টর্ক দিয়ে করতে পারবো না?
ও স্যার টর্ক দিলে তো তাহলে টর্কের ক্ষেত্রে হলো শিয়ার স্ট্রেস ম্যাক্সিমাম তাহলে সেন্টারে হবে, আর
কেন
যদি
শিয়ার স্ট্রেস ম্যাক্সিমাম সেন্টারে কেন?
না সেন্টারে না, সরি আপার লেয়ার হবে স্যার।
ক্রস সেকশন ওয়াইজ তো কোনো ভ্যারিয়েশন থাকবে না।
না না না
না স্যার।
তাহলে আগের মতোই রয়ে যাবে,
সাপোর্টেই হবে স্যার,
সাপোর্টেই হবে।
এবার ভাবো তোমার তাহলে ফাইনালি তুমি ডিজাইন করবে, তাই তো, অ্যাজ এ ডিজাইনার, বাট ইউ আর ইন এ প্রবলেম বিকজ দেয়ার ইজ শিয়ার স্ট্রেস ডিউ টু টর্ক, there is normal stress due to axial, there is normal stress due to bending. How I will compare with the material property? Because material property either in normal or in shear is known to me. But here the stresses are combined in nature. If it is normal, if it is axial and bending alone, I have no problem because these two stresses are normal in nature. They either can be subtracted or added and can get a final normal stress value and compare with the material permissible normal stress. But when torsion is present along with either axial or bending or both, then one stress is normal in nature, another stress is shear in nature.
Then, sir, I think we have to calculate the equivalent bending moments, combining
Equivalent?
both bending moment.
Why not equivalent stress?
Sir, equivalent stress. This is the stress is will be, sir, in shared in nature. It will
Look,
not be.
look. When sigma 1 and sigma 2 were evaluated, it also considered the effect of shear stress, no?
Yes, sir.
So why not they are equivalent stress? They can be the equivalent stress of this sigma x, sigma y, and tau xy. Instead of sigma x, sigma y, look, follow my statement. I have applied a sigma x in the x direction, a sigma y in the y direction, and a tau xy in the shear nature. For design purpose, instead of applying this type of loading, if I would apply a sigma 1 value, that will damage the material with same rate, as because material behavior in case of design is governed by the maximum stress. The maximum stress generated by this combination sigma x, sigma y, and tau xy is given by this sigma 1. So can I say that this value of sigma 1 is the equivalent normal stress of a combination of sigma x, sigma y, and tau xy?
Yes, sir.
So we derive this member from the concept of principal stresses. Now as a designer, I will revisit it. I will relook it. I will redefine it. What is sigma 1? It is nothing but the equivalent normal of a combined sigma x, sigma y, and tau xy. It is equivalent normal. Why you are interested to equivalent normal? As because I have to compare with the normal stress permissible for the material, and that can be done only with some equivalent normal. Therefore, my interest as a designer.
Yes, sir.
So I will evaluate equivalent normal using the concept of principal stress whenever there are normal stress and shear stress present in the material. Not only normal stress in only one direction, but it can be in both the direction. Suppose in the case of this cantilever beam, look, there may be a bending moment in the other plane also. No, we can apply a lateral load which will create bending stress again, but maybe in other direction. So even in I can evaluate the equivalent normal stress in case of presence of sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. All the 6 stress components. Look, all these 6 stress components. Why I am telling 6? Are you not confused?
Sir, ছটা independent, বাকি তিনটা তো dependent.
So what maximum can happen? All these 6 independent components are there in the member due to certain type of loading. Something is generated from bending, something from normal, something from torque.
Means, sir, all are present, sir.
Suppose all are present. Even that will not make me confused, because I have expression in terms of sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau zx. I have expression available in the book for principal stresses. Do you agree or not?
Yes, sir.
So can I say, whatever may be the loading pattern, try to visualize, whatever may be the loading pattern, either it will be axial in nature, torsion in nature, or bending in nature. We have learned when bending load is applied, what types of stresses are developed, where, with which magnitude, which direction, we know it. We can calculate it. We know the effect of torsion in terms of shear stress. Okay, somebody can tell, sir, you are ignoring the shear stress due to bending. No, I am not ignoring. You know that there is a shear stress distribution, no? In case of bending load,
Yes, sir.
which is maximum at the center, minimum at the surface. I can ignore it only because it is in magnitude wise it is very low. If somebody is interested and to make it more accurate, he is always allowed to include that effect of shear stress in the member. I have no objection. But now I can tell you that whatever may be the nature of load in the member, designer's inspection will be what stress it is generating. What stress? Now, for bending to stress, he has to use My by I. From axial to stress, P by area. From torsion to stress, TR by J. So if a designer knows this formulation, he can convert a load into stress, modular level. Do you agree or not? Modular level. For torsion, what is the effect in stress that he can evaluate? For bending, what is the stress he can evaluate? And the variation of stress over the cross section over the points. He can visualize the stress distribution due to bending alone. He can visualize the stress distribution due to axial alone, due to torsion alone. Am I clear?
Yes, sir.
Yes.
Now, designer interest, which is the critical cross section, because ultimately final damage, final material response will be governed by the combined effect of all kinds of loading. And it is not that bending will develop some effect, then principal, then torsion, and they are separated by each other, they are independent to each other, so nothing will happen due to what is happening in bending. It is not the scenario. All things are combined. A mutual combined effect will be there. Because of that, designer should have a very introspection, clear view about the stress distribution, and it is very important task of a designer to identify the critical cross section and critical member, or sorry, critical point in the critical cross section where we should evaluate the stress, so that with minimum calculation we can do the requirement of design. Design requirement is that material should not fail. Designer requirement is not how fine, how accurately you have analyzed the stresses, everything. That is not the designer's role. Designer has to know that. But designer's ultimate deliverable is to ensure that member will sustain the load. And if he can do it by his intuition, by his common sense, by his judicial decision with minimum calculation, it will be appreciated. It is not that you have derived stresses at millionth of points. Now, among them, you have used the Excel file, found out the maximum stress, then only you have designed. You will not be credited. But if designer has the insight, if he has the knowledge, and if he has applied over the total stress scenario by logic, he has segregated the unnecessary points, reduced the calculation, just calculating only in one cross section at a one point, evaluating the equivalent stress, comparing with the material property, finish the design in a 3 or 2 papers, he will be appreciated. Do you agree or not?
Yes, sir.
And for that, you should have this insight related to stress scenario within the member. Am I right or not?
Yes, sir.
বলো, কেউ কিছু বললে?
No, sir.
আমি কি বোঝাতে পারছি আমরা কি ভাবছি বা কি করতে
Yes,
চাই?
sir. Yes, sir.
Yes, sir. Yes, sir.
So first of all, I am trying to look you that you first have to do force analysis. আমি স্টার্ট করেছি লোড দেওয়া আছে, কিন্তু লোড পাওয়াটাও তো ওরকম অবভিয়াস হবে না। তোমরা ইঞ্জিনিয়ারিং মেকানিক্সে ফ্রি বডি ডায়াগ্রাম করেছো, তাই না?
Yes, sir.
And from that analysis, you actually identified there the, considering the internal actions also, reaction also, the what are the forces to which a particular member within the system is subjected. First, that analysis is required, which is called force analysis. Now you know the load, considering inside load, that means internal reaction, external load, considering all these things, you know the load scenario for every member. From there, you have to convert the load into stress. There you require this knowledge. And now, knowing the total varied type of stress, you have to make equivalent. There you require the analysis of biaxial stress analysis or triaxial stress analysis. Is the task transparent to you?
Yes, sir.
A design is to be done. I know the given performance or system. From there, first of all, I have to identify the load, force analysis. Just if it is a problem that this is the member, these are the external loads. Now tell me, what is the load upon this particular link? Link is a part in the system. To what forces this link is subjected? This is an expertise. As a designer, you should have this expertise, force analysis. Am I clear?
Yes, sir.
As a designer, you should also have the knowledge that load does not determine the failure of a mechanical member. Rather, stress determines the failure of a mechanical member. It is a knowledge. Do you agree?
Yes, sir.
Yes, sir.
Suppose a material is given, cast iron or suppose mild steel. If I say, if I apply 30 kilonewton, can you tell whether it will fail or not? You cannot answer it. Answer may be yes, answer may be no. As because you do not know the geometry, you do not know the what stress will be developed. The answer is not known until stress is known. So can I say that load is not the factor for the decision making by the designer? Am I clear?
Yes, sir.
Therefore, load is to be converted into stress. When stresses are complex in nature, normal, shear, etc., then one kind of stress alone cannot answer your material failure point, whether it will fail or not. Because whether a member will fail under an axial load of 100 Newton, that depends upon is there any another kind of load present, or it is only if another kind of load is present, then at what tensile load it will fail depends upon what is the value of bending load at that moment. It is related to the presence of bending load, isn't?
Yes, sir.
So designer cannot answer only by one kind of stress. So what is the responsibility? To find out the equivalent stress. A single member of stress which can determine the failure. I am right?
Yes, sir.
And what is available in material science? Material science says that, okay, in this particular grade of material, if the value of normal stress exceeds this value, you can assume that failure will occur. This is the information. Therefore, it is the responsibility of the designer to evaluate equivalent normal stress. Otherwise, he cannot get the answer whether it will be failure or not. So now, combining all the stress components present in the material, you have to find out some equivalent normal stress. Do you agree or not? Hello?
Yes, sir.
Somebody can
Yes,
tell.
sir.
Somebody can tell. Is it true that in every situation only equivalent normal stress can give you the answer? My answer is no. Because there are material which do not fail because of the exceeding of normal stress with the permissible stress. Rather, shear stress exceeds the permissible limits. So what is the designer role? He has also to be he has to evaluate the maximum shear stress due to combined stress. And we have that formula. We know these tau 1, 2, they are the extreme shear stress values, no? Tau 1, 2, tau 2, 3, tau 3, 1. So if all the normal stresses and shear stresses are known, we can convert it into a single shear stress, which can be compared with the material permissible shear stress, and designer can take decision whether it will be failure or not. Am I right or not?
Yes, sir.
So what will be your viewpoint? That a designer should be able, first, force analysis, to convert force into stress, and to convert different combined stress into some equivalent normal stress or tau shear stress as per requirement. If the material is ductile in nature, then generally it fails in shear. If the material is brittle in nature, then it fails in normal. Suppose cast iron is your material. As a designer, you know, okay, this is the grade which falls under the category of brittle material. Okay, I will do the design based on normal. I will ignore shear. No fault at all. It is the designer's confidence. If somebody does their both normal and shear and can ask, sir, I have done both the things, so I should get more credit, I will not say no. Because you do not know that for brittle material only normal stress is sufficient for checking. It is your lack of knowledge, not your rather enhancement in the knowledge. As a designer, you should be confident. Okay, I know it. I know that for category of brittle material, checking by normal stress is sufficient, and I will do by this job. It is designer's confidence. And it is only possible if you are aware that what is the nature of material and which material fails under what type of stresses. This material science, knowledge regarding material science is required by the designer. And if designer knows it, he is confident. And if the material is ductile, some mild steel category, designer has to check with the shear stress. Instead of evaluating principal normals, principal stress, he will calculate the maximum shear stress and check it with the permissible shear stress of the material and make the design complete, finalize the dimension. This is the designer's role. And to implement this efficiently, you have to know the material science also, material behavior. Am I right?
Yes, sir.
I think this is sufficient, no, for your understanding, because I can help you only understanding, and then you have to go through books, and you can rather get more confidence by studying books. Is the points conveyed today sufficient for you? For stress analysis and etc. Why stress analysis is required? What should be the designer role? What you should go through into the books? You will read the books, but in what perspective? Is it clear to you or not?
Yes, sir. Yes, sir.
Yes, sir.
Are
Yes,
you
sir.
confident? Are you confident? Then I can leave the class.
Yes, sir.
Yes, sir.
Okay.
Yes.
So লাস্ট একটাই কথা, নেক্সট উইক থেকে ফিজিক্যাল ক্লাস হচ্ছে, তাই তো?
Yes, sir. Yes,
Yes,
sir.
sir.
Fortunately, sir.
সোমবার দিন 3:30 দেখা হচ্ছে, হ্যাঁ? আমি
Yes, sir.
Yes, sir.
মেটেরিয়ালটা আগে ক্লাসরুমে পাঠিয়ে দেবো।
স্যার ফাইনালি স্যার। স্যার যখন অফলাইন ক্লাস হবে তখন কি আপনি মেটেরিয়াল গুলো আমাদেরকে মানে জেরক্স বা প্রিন্ট আউট দেবেন, নাকি এরকম গুগল ক্লাসরুমে পোস্ট করবেন?
ওই খাটুনিটা আর খাটিও না, গুগল ক্লাসরুমে দিলে তোমরা নিজেরা প্রিন্ট আউট নিয়ে জেরক্স করে নিতে পারবে। আই থিঙ্ক
স্যার ক্লাসরুমে দিয়ে দিন স্যার।
হ্যাঁ স্যার।
আমি ক্লাসরুমে দিয়ে দেবো, প্রত্যেকটা মেটেরিয়াল পড়ানোর আগেই দিয়ে দেবো, যাতে তোমরা একটু দেখে আসতে পারো, সো দ্যাট ইউ ক্যান
Okay,
অ্যাপ্রিসিয়েট দ্য ক্লাস। তা নাহলে ওয়ান সাইডেড হয়ে যাবে, আমি ভুলভাল যা খুশি বকে যাব, ইউ হ্যাভ টু অ্যাকসেপ্ট ইট, ইউ ক্যানট চ্যালেঞ্জ মি।
Yes, sir. হ্যাঁ স্যার।
ঠিক আছে।
Thank you, sir. Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.